Welcome back to the course on audio signal processing for music applications. In the previous demonstration class, we talked about the harmonic plus residual model. We actually analyzed a sound with the model with the SMS tools, and we were able to identify the harmonics, subtract them from the original sound, and obtain a residual, which then we combined with the harmonics to obtain the original signal. In this demonstration class, we want to go a little bit beyond that by approximating the residual with the stochastic model. And in the case that the residual is close to a stochastic signal, then this will be a good representation, the harmonic plus the stochastic component to represent a sound. So let's start, and let's open the GUI of SMS tools. And we will start with the sound of the flute sound. Okay, so let's listen to this flute sound. Okay, so it's a very stable note, quite clearly defined the pitch. In fact, is an A4. And it clearly has some breathing quality that will be relevant for this idea of the stochastic component. In order to decide what window size, well, again, let's use the Blackman window. Since it's a stable sound, Blackman will be a good choice for being able to get low the side lobes and getting a good kind of signal to noise ratio in terms of the window. So in order to compute what is the best window size, so we'll have to just do 6, which is the number of beams of the Blackman window, times the sampling rate, 44,100, divide by the fundamental frequency of this sound. And this is an A4, so it's 440 hertz. Okay, so 601 would be a good window to use. Given that we really want to get a good resolution of the harmonics and try to minimize the rest of the components, and it's quite stable, we can afford to take a longer window maybe. So let's take 801 samples. The FFT size, again, let's we can take a bigger FFT so that we get a smoother spectrum, so 2048. Okay, and well, let's analyze just in the middle of the sound. This is a quite long sound, so let's do it like that. Okay, so this is the samples of the input signal, and the spectrum. We see quite well the low frequency harmonics, and similar to the organ sound that we analyzed before. Yeah, in the high frequency areas, there is quite a bit of kind of unstable or kind of very stochastic type of components that are not so clearly defined as partials. So they may be there might be some harmonics or partials, but they are kind of masked and are difficult to identify here. Anyway, so okay. So now let's just go directly to the harmonic model, and let's apply the same parameters. So 801, 2048. Now we have to choose the parameters for the peak detection and the harmonic detection. I don't think we need to go very much down in the spectrum for the harmonics, because as we saw, there is not that many. In terms of the duration of the harmonics, I think it's good to make sure that they are long. Is a stable note, so we might want to put like 0.2 in terms of the minimum duration. In terms of number of harmonics, there are clearly not that many, so I'm sure with 40 should be plenty. And we have to set the minimum and maximum fundamental so that 440 fits here. So I'm sure if we put 300 and 500 should be plenty. And the error for the pitch detection, well, let's take the default 7, and the deviation, let's start with this value, see what happens. Oh, and of course we need to get the flute sound. Okay, now we can compute it. Okay, so clearly we got quite a few harmonics and some here that appear and disappear. Of course, we have to realize that here we are just plotting the first 5,000 hertz. If we want to see more and what's going on in the higher frequencies, we should display it a little bit differently. Okay, so let's just listen to the result. Okay, that's pretty good. That's a quite accurate rendition of that. Of course, it's different from the original one. In fact, if we hear back the original, yeah, the original has a more brighter type of quality, and this is because it has all these other components. Of course, we can play around with these parameters, for example, to allow for more harmonics to appear. So, for example, if we allow, let's say, put 0.1 here, and we compute it again, yeah, now we are allowing these higher harmonics, which are very unstable, to appear sort of more. But of course, all these jumps are not really that good. So that means that these harmonics are not really stable, so they are really buried into the kind of the noise or this breath that we also hear. Okay, now we can go ahead and use the harmonic plus residual model, so we can listen to the residual. And let's again use the same parameters. The flute sound, let's put 800, let's put 2048, and in terms of the threshold, minus 80, the minimum duration, let's just put 0.2, number of harmonics, yeah, we don't need that many, and well, this will be okay, 350, 700, and this, I think, 7 was all right. And yeah, let's make it not as open in terms of the deviation as before. Let's just put maybe 0.02, see what happens. Okay, so here we see the original and the harmonics, and maybe we see a few more than before, and synthesize. So let's listen to the residual. Okay, that's a pretty nice residual, very. We hear the attack, and the attack, in fact, there is this red thing here that during the attack it's clear louder, this breath, and then it just sort of gets attenuated, and we hear a very clear breath noise throughout. Okay, so now, so this is very much an stochastic signal, let's say. It's very noisy, so that means that we can apply the stochastic analysis to that. So now let's use the harmonic plus stochastic model, and let's get the same type of parameters. Of course, we can play around these parameters to get better values, but the ones we chose, they looked okay. So let's put 0.2 here. Let's get the number of harmonics. Yeah, I think 40 harmonics, and this was all right. This was 7, and this was 0.02. Okay, now the parameter that is specific for the stochastic analysis is the stochastic approximation factor, and here by default is 0.1. So it means that it reduces the whole spectrum by 90%. So it's only it will quantize kind of the resolution to 1/10 of what it originally was. So let's just try this. Okay, so clearly now we see well, we see it differently, because in this one we are showing the range from 0 to 14,000 hertz. So in fact, we're seeing quite a bit more, so we see more of the stochastic component. But as we see, the harmonics are very much on the lower side. Above 5,000 hertz, there is not that much. There is some of these, but maybe even these lines should not be considered harmonics, and maybe they should be discarded. But let's listen to the stochastic component. Okay, of course we have lost like a little bit of the details that the residual had, but it definitely keeps this breathy noise. Of course, it's not that loud, so if we put it together with the original signal, with the harmonics, okay, so it sounds good, but clearly the harmonics are taking over and they are kind of masking quite a bit this stochastic component. We have to listen to it quite carefully if we want to be able to distinguish the stochastic component of this type of sounds. And that's basically all I wanted to say. Let's go back. So we have talked about the harmonic plus stochastic model, and we have used the SMS tools, the interface that has allowed us to play around with this model. And of course, the sound that this flute sound is in free sound. So hopefully that has given you a view of the potential of the harmonic plus stochastic model. It's a little bit different from the harmonic plus residual, but the main difference is that now with the stochastic representation of the residual, we will be able to do quite a bit of things. Next week, in fact, we're going to be doing transformations to these sounds, and the stochastic representation will allow us to do that, whether in residual would not be able to give us that flexibility. So anyway, so that's all for this demonstration class, and I hope to see you next lecture. Thank you very much.